Right now, buried inside a violent cloud of gas 160,000 light-years from Earth, a single star is burning with the ferocity of almost 7 million suns. It is so luminous that its own light is ripping it apart from the inside. Stellar physics says a star this massive should not be able to hold itself together. Radiation pressure should have shredded it during birth or blown away enough material to bring it back below the theoretical ceiling. Yet it persists, 200 times the mass of our Sun, defying the equations that govern every other star in the observable universe. Its name is R136a1, and its existence has forced astrophysicists to rewrite the rules of how stars are born, how they live, and how violently they die. If you enjoy journeys into the most extreme corners of the cosmos, consider tapping that like button and subscribing. Now, settle in and get yourself comfortable. Let's begin. There is a region of the southern sky where the universe is tearing itself apart and rebuilding at the same time. If you have ever stood beneath dark skies south of the equator and looked toward the constellation Dorado, you may have noticed a faint, ghostly smudge sitting just off the luminous band of the Milky Way. It does not look like much, a pale cloud-like patch, easily mistaken for a wisp of atmospheric haze or a defect in your vision. Most people glance past it without a second thought, but that smudge is not part of our galaxy. It is an entirely separate galaxy, a small, ragged, irregular companion called the Large Magellanic Cloud, orbiting the Milky Way at a distance of approximately 160,000 light-years. It contains roughly 30 billion stars. It has its own spiral structure, its own stellar populations, its own history of formation and evolution stretching back billions of years. And buried inside it, hidden within a storm of ultraviolet radiation and superheated gas, is the single most extreme star that human instruments have ever measured. Getting to that star requires first understanding the environment that produced it, because in astrophysics, extreme objects do not arise from calm surroundings. They emerge from chaos. And there is no region of chaos in the local group of galaxies more violent than the Tarantula Nebula. The Tarantula Nebula, formerly catalogued as 30 Doradus, is a star-forming region of almost incomprehensible scale. It sprawls across nearly 1,800 light-years of the Large Magellanic Cloud, a seething complex of molecular gas, ionized hydrogen, dust lanes, and newborn stellar clusters. Its luminosity is so extreme that it is visible to the naked eye from Earth despite lying in another galaxy entirely. No other star-forming region within millions of light-years comes close to matching its output. If you transplanted the Tarantula Nebula to the position of the Orion Nebula, the most prominent stellar nursery visible from the Northern Hemisphere, sitting roughly 1,340 light-years away, it would not simply be brighter than Orion. It would dominate the night sky. It would span an area larger than 60 full moons. It would cast visible shadows on the ground after sunset. The Tarantula is not just a nebula, it is a factory, an engine of star formation operating at a pace and intensity unmatched anywhere in our galactic neighbourhood. The reason for this ferocity lies in the conditions of the gas itself. The molecular clouds feeding the Tarantula are denser, more turbulent, and more compressed than typical star-forming regions. Supersonic shockwaves ripple through the gas, driven by the radiation and winds of the massive stars already born within the nebula. These shocks compress pockets of gas to critical densities, triggering gravitational collapse and igniting new rounds of star formation. The process is self-sustaining. Massive stars form, blast their surroundings with ultraviolet radiation and fast stellar winds, compress nearby gas clouds, and trigger the birth of even more massive stars. It is a feedback loop running at full throttle, and it has been operating for several million years. Within the Tarantula Nebula lies a region of particular intensity, the central ionizing cluster designated R136. The name is unremarkable, a catalogue entry from the Radcliffe Observatory in Pretoria, South Africa, assigned during a photometric survey of luminous stars in the Magellanic Clouds during the early 1960s. At the time, R136 appeared as a single, intensely bright source, far too luminous for any individual star. Astronomers assumed it was a compact star cluster, its individual members blurred into one brilliant smear by the combined effects of distance and atmospheric turbulence. They were partly right. R136 is indeed a cluster, but its most remarkable member turned out to be something that the models of the day said should not be possible. For decades, R136 remained an unresolved enigma. Ground-based telescopes lacked the angular resolution to separate individual stars in such a dense, distant cluster. The entire core of R136 subtended an angle on the sky smaller than 1 arcsecond, roughly equivalent to the apparent size of a coin viewed from 3 kilometers away. Atmospheric seeing blurred everything into a single luminous blob. Astronomers could measure the total brightness and spectrum of the cluster, but they could not determine whether that light came from one extraordinary star, 2 moderately extraordinary stars, or a dozen merely impressive ones. The breakthrough came with the Hubble Space Telescope. Orbiting above Earth's atmosphere, Hubble could resolve individual stars in the core of R136 for the first time. Observations in the mid-1990s, using Hubble's high-resolution cameras, revealed the cluster's true nature. A dense swarm of dozens of extremely massive, extremely hot, extremely luminous stars, packed into a volume only a few light-years across. The stellar density in the core of R136 is estimated at several thousand stars per cubic parsec, roughly 200 times denser than a typical OB association, and tens of thousands of times more crowded than the solar neighborhood, where the density is approximately 0.1 stars per cubic parsec. Stars that would each individually rank among the most massive in the Milky Way are jammed together in a space so tight that gravitational interactions between them are not just possible but inevitable. Among this extraordinary population, one star stood apart. Designated R136a1, the brightest component of the cluster's central concentration, it was flagged almost immediately as unusual. Its spectrum showed the telltale emission lines of a Wolf-Rayet star, broad, powerful features produced by fast-moving gas in an extremely dense stellar wind. But its luminosity was far higher than any Wolf-Rayet star previously observed. Even accounting for the possibility that it might be a binary 2 stars orbiting so close together that their light blended into a single source, the numbers were extraordinary. Initial estimates placed its luminosity in the range of several million times that of the Sun. No established category of star could comfortably accommodate an object this bright. The definitive study came in 2010. A team led by Paul Crowther at the University of Sheffield combined ultraviolet imaging from the Hubble Space Telescope with spectroscopic data from the Very Large Telescope at the European Southern Observatory's Paranal facility in Chile. They modelled the stellar atmosphere of R136a1 using sophisticated radiative transfer codes that simulate how photons interact with the hot, dense, expanding gas of the stellar wind. By matching the observed spectrum to their models, they derived the star's fundamental parameters: surface temperature, luminosity, radius, mass loss rate, and most critically, mass. The results sent a tremor through the astrophysics community. Crowther's team estimated the current mass of R136a1 at approximately 265 times that of our Sun, factoring in the mass already lost through its ferocious stellar wind over its lifetime. The implied birth mass exceeded 300 solar masses. The paper appeared in the monthly notices of the Royal Astronomical Society and quickly generated headlines around the world. The most massive star ever discovered, shattering records by a wide margin. But headlines and science operate on different standards. The astrophysics community greeted the result with a combination of genuine excitement and rigorous skepticism. Mass estimates for stars like R136a1 are not straightforward measurements. You cannot place a distant star on a balance. In the rare cases where a massive star is part of a well-characterized binary system, Its mass can be determined dynamically by observing the orbital motion of the two components and applying Kepler's laws. But R136a1 shows no clear evidence of a binary companion. Its mass must instead be inferred indirectly, through spectroscopic modelling and comparison with theoretical evolutionary tracks. This method involves several layers of assumption. The radiative transfer codes that simulate the stellar atmosphere depend on adopted values for wind clumping, chemical abundances, and the velocity structure of the outflow. Wolf-Rayet stars do not have neat photospheres like the Sun. Their surfaces are buried beneath dense, expanding winds that create a pseudo-photosphere, an effective surface that is actually the base of the outflow rather than a solid boundary. The properties you derive, temperature, radius, luminosity, depend on how you model this wind. Different codes using different assumptions can yield different answers. A shift in the adopted clumping factor can change the inferred mass loss rate by a factor of 2. A different treatment of line blanketing the cumulative absorption by millions of overlapping spectral lines from iron group elements can alter the derived temperature by thousands of Kelvin. And because luminosity depends on both temperature and radius, these uncertainties compound. The evolutionary track method introduces its own complications. Stellar evolution codes predict how a star of a given initial mass should appear at each stage of its life. Its temperature, luminosity, surface composition, and mass loss history as it ages and burns through its nuclear fuel. By matching the observed properties of R136a1 to these tracks, astronomers can estimate where the star currently sits in its evolutionary journey and infer its mass. But the tracks themselves depend on input physics, nuclear reaction rates, opacity tables, convective mixing prescriptions, rotation, and mass loss rates. Different groups using different input physics produce different tracks, which yield different mass estimates for the same observed star. This is why the mass of R136a1 has been revised repeatedly since 2010. Subsequent studies using updated atmosphere models, revised clumping prescriptions, and improved opacity calculations brought the mass estimate down from the initial 265 solar masses. The VLT Flames Tarantula Survey, a landmark spectroscopic campaign that observed over 800 massive stars across the entire 30 Doradus region, provided high-quality, multi-epoch spectra that allowed researchers to apply consistent modelling to R136a1 and its cluster siblings. Using both the CMFGen and POWR radiative transfer codes with updated physics, the survey team derived a current mass closer to 200 solar masses. Then came the James Webb Space Telescope. In 2023 and 2024, Webb's near-infrared spectrograph observed the core of R136 at wavelengths that Hubble could not access. Infrared light penetrates the dense stellar wind more effectively than ultraviolet or optical radiation, probing deeper into the outflow structure and providing tighter constraints on the wind density profile, clumping geometry, and terminal velocity. These data allowed researchers to partially break the degeneracies that had plagued earlier modelling efforts. Mass estimates published since 2022 have placed R136a1 at approximately 200 solar masses in some analyses and as high as 290 in others, depending on the atmosphere code, the adopted helium abundance, and whether the mass is derived from spectroscopic modelling or evolutionary tracks. The range spans roughly 170 to nearly 300 solar masses, a wide spread that reflects genuine uncertainty in the underlying physics rather than imprecision in the instruments. Even the lower end of that range, 170 solar masses, is extraordinary. It places R136a1 well above the classical theoretical ceiling for stellar mass. The upper end approaches the revised limits from modern formation simulations. And every analysis, regardless of methodology, agrees on one fundamental point. R136a1 is the most massive star with a reliable spectroscopically derived mass measurement. Other candidates exist: stars in the Arches cluster near the galactic center, or the enigmatic object WR42e in the Tarantula Nebula, but none have been studied with the same depth, the same multi-wavelength coverage, or the same level of scrutiny as R136a1. It is the benchmark, the test case, the object against which all theoretical predictions for extreme stellar mass are calibrated. A lingering question haunted the measurements for years. Was R136a1 truly a single star? The core of R136 is so densely packed that even Hubble's resolution could not entirely rule out a very close companion. If two massive stars, say 130 solar masses, each orbited each other at separations too small for telescopes to resolve, their combined light would mimic a single star of 260 solar masses. This binary contamination hypothesis was taken seriously and tested repeatedly. Multiple observational campaigns searched for the signatures of binarity. Spectroscopic monitoring looked for radial velocity shifts, periodic changes in the wavelengths of absorption and emission lines that would indicate one star moving toward Earth while the other moved away as they orbited their common center of mass. No significant periodic signal was detected across years of monitoring. Hubble's fine guidance sensors searched for the subtle positional wobble that a massive companion would induce. Nothing was found above the detection threshold. Interferometric observations from the Very Large Telescope probed angular separations far smaller than the seeing limit of ground-based telescopes. The star remained consistent with a single-point source. The scientific consensus today is firm. R136a1 is a single star, or at most a system where any companion contributes negligibly to the total luminosity and mass. The monster is not an illusion created by blended binary light. It is one object, one stellar furnace, holding itself together under conditions that test the fundamental equations of stellar structure. The luminosity numbers deserve particular attention because they reveal the physical regime this star inhabits. R136a1 radiates at approximately 6.2 million times the luminosity of our Sun. This figure, derived from integrating the star's energy output across all wavelengths, including the far ultraviolet where most of its radiation emerges, places it among the 3 or 4 most luminous stars known in the observable universe. At a surface temperature of approximately 53,000 Kelvin, nearly 10 times hotter than the solar surface, the peak of its radiation lies deep in the ultraviolet, far beyond what human eyes can detect. If you could see in ultraviolet wavelengths, R136a1 would outshine everything else in the Large Magellanic Cloud by an enormous margin. This luminosity is not merely impressive, it is physically consequential. A star this luminous is not merely bright, it is fighting itself, generating so much radiation that it threatens to push its own surface into space. There is a threshold beyond which a star's light becomes its own undoing. That threshold has a name, an equation, and a history that reaches back a century. Understanding it is the key to understanding why R136a1 matters, not as a curiosity, not as a record holder, but as a genuine challenge to our models of how stars are born, how they sustain themselves, and where the upper boundary of stellar existence actually lies. R136a1 is also classified as a WN5H star, a specific subtype of Wolf-Rayet star. The Wolf-Rayet classification denotes stars with extremely strong broad emission lines in their spectra, produced by fast-moving material in a dense stellar wind. The WN indicates a nitrogen-rich spectrum, meaning the star's wind is dominated by nitrogen emission rather than carbon. The 5 refers to the ionization level of the nitrogen lines, indicating very high excitation temperatures. And the H critically indicates that hydrogen is still present in the spectrum. This last detail matters more than it might seem. Classical Wolf-Rayet stars are evolved objects. They are massive stars that have shed their outer hydrogen envelopes through intense stellar winds, exposing the helium-burning or nitrogen-rich layers beneath. They represent a late stage of stellar evolution, burning through their remaining fuel on timescales of a few 100,000 years before exploding as supernovae. But WNH stars like R136a1 are different. The presence of hydrogen in their spectra indicates that these objects have not yet stripped away their outer layers. They are still on the main sequence, still burning hydrogen in their cores. They look like Wolf-Rayet stars because their surface temperatures and wind densities are extreme enough to produce Wolf-Rayet emission features, but they are actually core hydrogen-burning objects, the most massive main sequence stars in existence. This distinction reshapes the interpretation of R136a1's properties. If it were a classical, hydrogen-depleted Wolf-Rayet star in an advanced evolutionary stage, its current mass would represent a heavily reduced remnant of a once larger object. The birth mass implications would be even more extreme, but as a hydrogen-rich main sequence star, R136a1 is closer to its birth mass than a stripped Wolf-Rayet would be. It has lost mass through its wind, certainly, but it still retains a substantial hydrogen envelope. The mass we measure today is closer to the mass it was born with, modified by millions of years of wind losses, but not yet reduced by the dramatic stripping that characterizes later evolutionary phases. The cluster environment surrounding R136a1 provides essential context. The R136 cluster is young, approximately 1 to 2 million years old, based on the evolutionary stages of its most massive members. This is extraordinarily young by stellar standards. Our Sun has been burning for 4.5 billion years. The oldest stars in the Milky Way's halo exceed 13 billion years. A cluster that formed merely 1 to 2 million years ago is a newborn in cosmic terms, still embedded in the remnants of the molecular cloud from which it coalesced. Within a few parsecs of R136a1, the total stellar mass is estimated at approximately 50,000 solar masses, distributed across roughly 100,000 individual stars, ranging from subsolar dwarfs to the hypergiants at the core. The concentration of mass toward the center is extreme. The most massive stars are 136, a 2 and a 3 at roughly 150 and 130 solar masses, all sit within the innermost fraction of a parsec, concentrated at the gravitational center of the cluster. The sheer number of very massive stars in R136 is itself unusual. The cluster contains at least a dozen stars above 50 solar masses and several above 100. Most star-forming regions in the Milky Way produce at most 1 or 2 stars above 50 solar masses. The Tarantula Nebula's ability to produce so many extreme objects in a single cluster is directly related to the density and turbulence of its parent molecular cloud. Higher gas pressures, stronger shocks, and deeper gravitational potential wells all favour the formation of more massive stars. R136 did not create R136a1 in isolation. It created an entire population of extreme objects, with R136e1 representing the most extreme member of an already extreme distribution. This sets up the fundamental question that drives the rest of the episode. R136i1 is not simply the largest star ever measured. Size alone, radius, volume, the amount of space an object occupies is not what makes it significant. Several red supergiants and hypergiants dwarf 136a1 in physical radius. Stephenson 2-18, UY Scuti, and others are vastly larger in spatial extent. But radius is not the relevant parameter here, mass is. And mass, in the context of stellar physics, is everything. Mass determines how luminous a star will be. Mass determines how hot its core burns. Mass determines how quickly it exhausts its fuel. Mass determines whether it can sustain itself against its own radiation, or whether it will blow itself apart. And mass determines where a star sits relative to the theoretical ceiling that physics imposes on stellar objects. That ceiling is not arbitrary. It arises from the deepest equations governing the interaction between matter and radiation inside a star. It is set by a balance point where the outward push of photons exactly matches the inward pull of gravity. Cross that line, and a star cannot hold itself together. The existence of R136e1 Sitting at or near that boundary forces astrophysicists to confront a precise and uncomfortable question. Where exactly does that line fall? And why does this star appear to be standing on it rather than being destroyed by it? The answer begins with an equation written a century ago by a physicist who understood, before anyone else, that starlight could be a force strong enough to tear a star apart. In 1916, Arthur Stanley Eddington sat in the quiet of the Cambridge Observatory and began wrestling with a question that would define stellar astrophysics for the next century. He wanted to understand the internal structure of stars, not just their surfaces, which astronomers could observe through telescopes, but the hidden physics operating deep inside, where temperatures reached millions of degrees and pressures crushed matter into states that no laboratory on Earth could replicate. Eddington was not content to simply catalogue the brightness and colour of stars. He wanted to know what held them together, and in pursuing that question, he discovered something profound. Stars carry within them the mechanism of their own destruction. The insight was deceptively simple. A star generates energy through nuclear reactions in its core. That energy takes the form of photons, particles of light, which carry both energy and momentum. As these photons travel outward from the core toward the surface, they interact with the stellar material they pass through. They are absorbed by atoms, re-emitted, scattered by electrons, redirected, and delayed. Each interaction transfers a tiny amount of momentum from the photon to the matter it strikes. One photon pushing on one atom is negligible, but in the core of a massive star, trillions upon trillions of photons stream outward every fraction of a second, each one delivering a microscopic push to the gas it encounters. The cumulative effect of all those tiny pushes is a macroscopic force, radiation pressure directed outward, opposing the inward pull of gravity. Eddington realized that for any given mass of star, there exists a luminosity at which the outward radiation pressure exactly balances the inward gravitational pull at the stellar surface. Below this luminosity, gravity wins. The star holds together comfortably, its outer layers pressed inward by gravitational force that comfortably exceeds the outward photon push. Above this luminosity, radiation wins. Photons shove the surface material outward faster than gravity can pull it back. The outer layers of the star get blown away. The star cannot maintain its structure. It begins to disintegrate from the outside in. This critical luminosity is called the Eddington luminosity, and the corresponding limit on mass is called the Eddington limit. The mathematics are elegant. The Eddington luminosity depends on just two quantities: the mass of the star and the opacity of the stellar material, a measure of how effectively matter absorbs and scatters radiation. Higher mass means stronger gravity, which permits a higher Eddington luminosity before radiation overwhelms it. Higher opacity means photons push harder on each gram of material, which lowers the Eddington luminosity. The equation balances gravity against radiation pressure and draws a line that no stable star should be able to cross. For a star composed of fully ionized hydrogen, the simplest possible composition, the dominant source of opacity is electron scattering. Free electrons in the stellar plasma scatter photons efficiently, transferring momentum from the radiation field to the gas. This electron scattering opacity is nearly constant regardless of temperature or density, which gives the Eddington limit a clean, predictable form. For a star of 100 solar masses, the Eddington luminosity works out to roughly 3.2 million times the luminosity of the Sun. For 200 solar masses, it is approximately 6.4 million solar luminosities, R136a1. With its luminosity near the Eddington value for a star of its mass, is burning at approximately 70 to 80% of that critical threshold, close enough that even modest perturbations could push the outer layers toward instability. It is operating almost exactly at the threshold where its own light could tear it apart. This proximity to the limit is not a coincidence. It is a direct consequence of how stellar luminosity scales with mass. For main sequence stars in the intermediate mass range between roughly 2 and 50 solar masses, luminosity increases approximately as mass raised to the power of 3.5. This means that doubling the mass produces roughly 11 times the luminosity. Tripling the mass yields about 47 times the luminosity. The relationship is steep but manageable at moderate masses. A 10 solar mass star is comfortably below its Eddington luminosity. A 50 solar mass star is well below it, though the margin has narrowed significantly. But as mass climbs above 50 solar masses, the luminosity-mass relationship steepens further due to the increasing dominance of radiation pressure in the stellar interior. Above roughly 100 solar masses, the relationship approaches something closer to a linear proportionality. Luminosity scales almost directly with mass rather than as a steep power law. This flattening occurs because radiation pressure becomes the dominant support mechanism in the stellar interior. The star is no longer supported primarily by the thermal pressure of hot gas. It is held up by the sheer force of its own light, pushing outward against gravity. The internal structure becomes radiation-dominated, and the luminosity asymptotically approaches the Eddington value. This convergence between actual luminosity and Eddington luminosity is what creates the effective mass ceiling. As you add mass to a star, its luminosity approaches the Eddington limit more and more closely. At some point, the margin between actual luminosity and the Eddington threshold becomes so thin that even modest perturbations, a slight change in opacity, a fluctuation in the energy generation rate, a wave propagating through the stellar envelope can push the star over the edge. The outer layers become unbound. Material streams away from the surface. The star loses mass until it drops back below the limit. Then the process repeats. The star oscillates around the Eddington threshold, shedding mass in bursts, unable to sustain itself above a certain value. This is not merely theoretical prediction. It is observed behavior, dramatic, violent, and recorded in the historical literature. The class of stars known as luminous blue variables represents the most direct observational evidence for what happens when a star approaches or exceeds its Eddington luminosity. These are among the most luminous and unstable stars in the galaxy, and they spend their lives oscillating between periods of relative calm and episodes of catastrophic mass ejection. The most famous and best studied example is Eta Carinae, a hypergiant system located roughly 7,500 light-years from Earth in the Tarantula Nebula. In the 1840s, Eta Carinae did something extraordinary. Over a period of approximately 20 years, the star erupted in what astronomers now call the Great Eruption, an event so violent that it briefly made Eta Carinae the second brightest star in the entire night sky, outshone only by Sirius, which is over 1,000 times closer to Earth. At its peak in 1843, Eta Carinae radiated with an estimated luminosity exceeding 50 million times that of the Sun. For a few years, a star that most humans had never heard of blazed in the southern sky with a brilliance that demanded attention from every observatory in the southern hemisphere. Sailors used it for navigation. Astronomers recorded its brightening with a mixture of fascination and confusion. Nobody at the time understood what they were witnessing. What they were witnessing was the Eddington limit in action. During the Great Eruption, Eta Carinae expelled somewhere between 10 and 45 solar masses of material, an almost incomprehensible quantity, equivalent to the total mass of 10 to 40 entire stars like our Sun, launched into space in a matter of years. This material did not simply evaporate. It was blasted outward at speeds exceeding 600 kilometers per second, forming a massive expanding cloud of gas and dust that is still visible today. That cloud, known as the Homunculus Nebula, is one of the most photographed objects in modern astronomy. It consists of two enormous bipolar lobes, each roughly 1 light-year across, expanding outward from the central star like the two halves of an hourglass. The lobes are rich in nitrogen, a signature of CNO processed material dredged from deep within the star's interior during the eruption. Dust grains condensing within the expelled gas scatter and absorb the star's light, making the homunculus one of the brightest infrared sources in the sky. The total energy released during the Great Eruption approached that of a supernova, yet the star survived. Eta Carinae did not explode. It shed a significant fraction of its mass, dimmed dramatically in the decades following the eruption, and then settled into a lower but still extraordinary luminosity. Today, it radiates at roughly 5 million solar luminosities, still among the most luminous stars in the Milky Way. It has experienced smaller eruptions since the Great Eruption, including a lesser event in the 1890s, suggesting that the star continues to flirt with instability. Astrophysicists interpret these episodes as repeated encounters with the Eddington limit. The star's luminosity periodically approaches or exceeds the threshold where radiation pressure overwhelms gravity at the surface. The outer layers become unbound, material streams outward in a violent ejection, the star loses mass, its luminosity drops back below the limit, and it stabilizes temporarily. Then the cycle begins again. Eta Carinae is not unique. Other luminous blue variables scattered across the Milky Way and nearby galaxies show similar behavior at smaller amplitudes. S Doradus in the Large Magellanic Cloud, P Cygni in our own galaxy, and AG Carinae, which was featured as the Hubble Space Telescope's 31st anniversary image precisely because of the spectacular nebula created by its own past eruptions. Each of these stars occupies the same dangerous region of the luminosity mass diagram, close to the Eddington limit, prone to instability, shedding mass in episodic bursts that prevent them from remaining far above the theoretical ceiling for extended periods. This eruptive mass loss represents one of the key mechanisms that enforces the upper mass boundary. It acts as a pressure valve. When a star's luminosity climbs too close to the Eddington threshold, the envelope becomes unstable, mass is expelled, and the star retreats to a safer configuration. The process is violent, unpredictable, and poorly understood in its details, but its net effect is clear. It grinds massive stars down, preventing them from sustaining masses far above the limit for long. And it raises a pointed question about R136a1. If Eta Carinae, at roughly 100 solar masses, already experiences such dramatic instability, how does a star at 200 solar masses avoid tearing itself apart entirely? Understanding why the ceiling exists at a specific mass value requires following the energy from its nuclear source to the stellar surface. The engines driving the most massive stars differ fundamentally from those powering stars like our Sun. In the solar core, hydrogen fusion proceeds primarily through the proton-proton chain, a sequence of reactions where individual protons combine step by step to build helium nuclei. This process is relatively slow because the first step, two protons fusing to form a deuterium nucleus, requires one proton to spontaneously convert into a neutron through the weak nuclear force. The reaction rate is modest, which is why the Sun burns steadily and will continue doing so for billions of years. In stars above roughly 1.3 solar masses, a different reaction pathway takes over, the carbon-nitrogen-oxygen cycle, universally abbreviated as the CNO cycle. In this process, carbon nuclei serve as catalysts. A carbon-12 nucleus absorbs a proton, transforms through a series of intermediate steps involving nitrogen and oxygen isotopes, and eventually returns to carbon-12 while releasing a helium-4 nucleus as the net product. The carbon is not consumed. It facilitates the fusion of hydrogen into helium, acting as a nuclear middleman. The CNO cycle has a critical property that separates it from the proton-proton chain. Its reaction rate is extraordinarily sensitive to temperature. While the proton-proton chain rate scales roughly as temperature to the fourth power, the CNO cycle rate scales as temperature to approximately the 16th power. This means that a 10% increase in core temperature produces a roughly 4.6-fold increase in the CNO energy generation rate. A 20% increase produces roughly 18 times more energy. The sensitivity is extreme. This temperature dependence has a structural consequence. In a star powered primarily by the CNO cycle, the energy generation is concentrated in a very small central region where temperatures are highest. The luminosity produced in this tiny core is so intense relative to the volume through which it must pass that radiation alone cannot transport it outward efficiently. The temperature gradient becomes too steep. The gas becomes convectively unstable, hot blobs of material rise, cool blobs sink, and turbulent convective currents carry energy outward through bulk motion of the gas rather than through photon diffusion. The cores of massive stars are convective, churning cauldrons where nuclear processed material gets mixed outward and fresh hydrogen gets dragged inward. This convective core has a direct impact on the star's mass limit. Convective mixing brings fresh fuel into the burning region, allowing the star to sustain higher energy generation rates than it could if the core were purely radiative. But it also means that the star's luminosity is controlled by the total mass of the convective core, which itself grows with stellar mass. As the star's total mass increases, the convective core encompasses a larger fraction of the total stellar volume. For the most massive stars, the convective core can extend to more than 80% of the star's total mass. Nearly the entire star participates in nuclear burning either directly or through convective transport of processed material. Above the convective core lies the stellar envelope, the outer layers, that are not actively burning nuclear fuel but through which the tremendous luminosity generated below must pass. In the most massive stars, this envelope is supported almost entirely by radiation pressure. The gas pressure contribution becomes subordinate. The envelope exists in a precarious state, a relatively thin shell of material suspended above the nuclear furnace by the upward push of photons streaming through it. This is where opacity becomes decisive. The opacity of stellar material is not constant. It varies with temperature, density, and chemical composition. At certain temperatures, specific elements become partially ionized, meaning their electrons are in configurations that are exceptionally efficient at absorbing photons. Iron is the most important culprit. At temperatures near 150,000 to 200,000 Kelvin, iron ions possess electron configurations that create a forest of overlapping absorption lines. The cumulative effect is a dramatic spike in opacity, a zone where photons get trapped far more efficiently than in the surrounding layers. This iron opacity bump, located in the subsurface layers of the most massive stars, creates a bottleneck for energy transport. Photons streaming outward from the core hit this high opacity zone and get partially trapped. The local radiation pressure spikes. If the luminosity is high enough close to the Eddington limit, this opacity-driven pressure enhancement can destabilize the overlying layers. The material above the iron bump gets pushed outward, initiating a density wave that propagates toward the surface. In extreme cases, this instability drives mass ejection. Layers of the star are inflated, become gravitationally unbound, and stream away as a wind or eruptive outflow. This opacity-driven instability is one of the principal mechanisms that enforces the upper mass limit. Even if a star manages to form with a mass above the classical ceiling, the iron opacity bump in its envelope acts as a self-regulating mechanism. Every time the star's luminosity approaches the Eddington threshold at the iron bump, instabilities develop and mass gets expelled. The star sheds material until its luminosity drops below the local Eddington limit at the opacity peak. It is a thermostat crude, violent, but effective at preventing stars from remaining far above the mass boundary for extended periods. This brings us to the second great enforcer of the mass ceiling, mass loss through radiatively driven stellar winds. Every star, with a surface temperature above roughly 25,000 Kelvin, produces a continuous outflow of material accelerated by radiation pressure on spectral absorption lines. The mechanism is distinct from the bulk radiation pressure described by the Eddington limit. Here, individual photons are absorbed by specific ions in the stellar atmosphere, typically metals like iron, carbon, nitrogen, and oxygen, transferring their momentum to those ions. The accelerated ions collide with surrounding hydrogen and helium atoms, dragging the entire atmosphere outward. The result is a supersonic wind streaming away from the stellar surface at velocities ranging from 1,000 to 3,000 kilometers per second. The strength of this wind depends on several factors. Luminosity is primary. More photons mean more momentum available to drive the outflow. Surface temperature matters because it determines which ions are present and how efficiently they absorb radiation. And chemical composition is crucial, because the wind is driven by metal absorption lines. A star with more metals in its atmosphere has more absorption lines, captures more photon momentum, and drives a stronger wind. A metal-poor star with fewer absorbing ions drives a weaker wind and retains more of its mass. For the most massive and luminous stars in the local universe, mass loss rates through stellar winds reach values that are almost difficult to believe. A star at 100 solar masses with a surface temperature of 45,000 Kelvin can lose mass at a rate of roughly 10 to the negative 5 solar masses per year. Written out, that is 100,000th of a solar mass annually, seemingly tiny, but accumulated over a stellar lifetime of 2 to 3 million years, it adds up to 20 to 30 solar masses lost to the wind. The star literally evaporates, shedding a significant fraction of its birth mass into the surrounding interstellar medium. For the most extreme objects, the mass loss rates are even higher. R136a1 loses mass at approximately 5 times 10 to the negative 5 solar masses per year. At this rate, the star expels roughly 1 solar mass every 20,000 years. Over its expected main sequence lifetime of approximately 2 million years, it will lose on the order of 100 solar masses through its wind alone, potentially more if the wind was stronger earlier in its life, when the star was more massive and more luminous. This wind-driven mass loss creates a feedback loop that works alongside the Eddington limit to enforce the mass ceiling. A massive star forms with a high birth mass. Its extreme luminosity drives a powerful wind that begins stripping material from the surface immediately. As the star loses mass, its luminosity decreases slowly, because luminosity depends on the mass of the convective core, which is buffered from surface mass loss. But over millions of years, the core mass does decrease, the luminosity drops, and the wind weakens. The star converges toward a lower mass where it can sustain itself in equilibrium. The timescale of this convergence depends on the initial mass and the mass loss rate. For a star born at 300 solar masses with a mass loss rate of 10 to the negative 4 solar masses per year, plausible for the most extreme objects, the star would shed 100 solar masses in 1 million years, arriving at 200 solar masses by midlife. This is precisely the regime where we observe R136a1, a star that may have been born significantly more massive than it is today, ground down by its own wind to a mass that, while still extraordinary, is lower than its birth value. The classical theoretical prediction, established through work by numerous groups throughout the 1980s and 90s, placed the effective upper mass limit at approximately 150 solar masses for stars with solar-like chemical composition. This number was not derived from a single equation, but from the convergence of multiple constraints. The Eddington limit for electron scattering opacity, the ion opacity-driven envelope instabilities, radiatively driven wind mass loss over stellar lifetimes, and the statistical arguments from observed stellar populations. The most massive, well-measured stars known at that time fell below or near this boundary, which lent confidence to the theoretical prediction. But this prediction carried important caveats that were sometimes understated. The 150 solar mass ceiling was calculated for a specific metallicity, roughly solar, and for non-rotating stellar models. Both assumptions affect the results significantly. Metallicity alters the mass ceiling through 2 distinct pathways. First, lower metallicity reduces the line driving force of the stellar wind, because fewer metal ions are available to absorb photon momentum. This means metal-poor stars lose mass more slowly and can retain higher masses throughout their lives. A star born at 250 solar masses in a metal-poor environment might lose only 50 solar masses through its wind over its lifetime, ending at 200 solar masses still viable. The same star born in a metal-rich environment might lose 150 solar masses, ending at 100 pushed below the classical ceiling by its own wind. Second, lower metallicity reduces the electron scattering opacity slightly and modifies the ion opacity bump, shifting the Eddington limit upward and allowing the star to sustain a higher mass before encountering catastrophic instability. The Large Magellanic Cloud, where R136a1 resides, has a metallicity approximately half that of the solar neighbourhood. This is low enough to meaningfully weaken the stellar wind and raise the effective Eddington limit, but not so low that the chemistry is dramatically different. The reduced metallicity means that the mass ceiling in the Large Magellanic Cloud should be higher than in the Milky Way, perhaps approaching 200 or 250 solar masses, depending on the model. This is precisely the range where R136a1 sits, which is both reassuring and frustrating. It suggests the star is near the limit for its environment, but does not clearly violate it. Stellar rotation introduces another complication. A rapidly rotating massive star experiences centrifugal support that partially counteracts gravity at the equator. This effective reduction in surface gravity lowers the local Eddington luminosity, making the star more susceptible to radiation-driven mass loss at lower luminosities than a non-rotating model would predict. Rotation also drives internal mixing processes, meridional circulation and shear instabilities that transport fresh hydrogen into the burning core and processed helium and nitrogen outward toward the surface. This mixing extends the main sequence lifetime and alters the relationship between surface properties and core mass. The effect of rotation on the upper mass limit is complex and model-dependent. Some calculations find that rapid rotation lowers the effective ceiling by enhancing mass loss through rotationally modified winds. Others find that the extended core hydrogen burning lifetime allows the star to appear more luminous for longer, mimicking a higher mass non-rotating star. The interplay between rotation, mixing, and mass loss creates a multi-dimensional parameter space, where the upper mass limit is not a single number, but a surface defined by mass, metallicity, and rotation rate simultaneously. Modern stellar evolution models, incorporating updated opacity tables, rotation, and metallicity-dependent mass loss prescriptions, have pushed the theoretical upper mass boundary upward from the classical 150 solar masses. Groups using the Geneva Stellar Evolution Code, the MESA code, and the Bonn evolutionary models all find that stars with masses up to 250 or even 300 solar masses can form and survive on the main sequence under favourable conditions, low metallicity, moderate rotation, and formation in a dense cluster environment where accretion can proceed efficiently despite radiation pressure. But can form and survive does not mean commonly form and survive. The probability drops steeply with increasing mass. A star at 150 solar masses is rare. A star at 200 solar masses is exceptionally rare. A star at 300 solar masses, if it exists at all, represents the extreme tail of a distribution that falls off so sharply that you might need to search thousands of massive star clusters to find a single example. The upper mass limit is not a brick wall where stars abruptly become impossible. It is more accurately described as a steep cliff, a region where the probability of a star forming and surviving at a given mass plunges rapidly towards zero without ever quite reaching it. This probabilistic nature of the mass ceiling is critical for interpreting R136a1. The star does not need to violate physics to be surprising. It merely needs to be rare, and it is. The question is whether it is rare in a way that current models can accommodate, sitting on the tail of a known distribution, or rare in a way that reveals a gap in the models, occupying a region of parameter space that the theory cannot populate at all. That distinction depends on the precise mass loss history, and the precise formation conditions, all of which carry uncertainties that are still being narrowed by ongoing observations. There is one more constraint worth examining before moving forward: the formation barrier. Even if a star can survive at 200 solar masses once it exists, the process of assembling that much material faces its own Eddington-like problem. A growing protostar becomes luminous long before it reaches the main sequence. By the time it has accreted 20 or 30 solar masses, its luminosity is already significant. The radiation from the protostar pushes back against the infalling gas, creating a radiation pressure barrier that opposes further accretion. In the simplest models, spherically symmetric infall onto a luminous central source, this barrier halts accretion at around 20 to 40 solar masses. The protostar's own light prevents it from growing larger. This formation barrier was once considered as fundamental as the Eddington limit itself. If stars cannot accrete above 40 solar masses, the question of whether they can survive above 150 solar masses is irrelevant. They can never get there. The mere existence of stars above 100 solar masses was, for decades, a challenge to formation theory as much as to stellar structure theory. The resolution of this formation barrier came through increasingly realistic simulations that abandoned the assumption of spherical symmetry. Real star formation is messy. Gas does not fall inward uniformly from all directions. It channels through a flattened accretion disk, concentrating the infall into a narrow equatorial plane, while radiation escapes preferentially through the polar directions. This geometric asymmetry allows accretion and radiation to coexist. Mass flows in through the disk while energy flows out through the poles. The star can continue growing even as its luminosity climbs, because the radiation and accretion occupy different solid angles. Turbulence in the infalling gas adds another escape route. Real molecular clouds are chaotic, threaded with supersonic turbulent motions that create dense knots and filaments. These overdense clumps can penetrate radiation barriers that would halt a smooth, uniform flow. Rayleigh-Taylor instabilities develop at the interface between outward radiation pressure and inward gravitational infall, allowing fingers of dense gas to punch through the radiation field and deliver mass directly to the protostar or its accretion disk. This process is episodic and stochastic accretion does not proceed smoothly, but in bursts as successive dense clumps break through the radiation barrier. Together, disk accretion and turbulent clump penetration raise the formation ceiling dramatically. Modern three-dimensional radiation hydrodynamic simulations, the most computationally demanding calculations in stellar astrophysics, show that stars can accrete up to several hundred solar masses under favorable conditions. The simulations are not unlimited. They require specific initial conditions. Very dense molecular cloud cores with masses exceeding 1,000 solar masses, high turbulent Mach numbers, and short free-fall timescales that allow the protostar to accumulate mass before feedback processes shut off the supply. These conditions are rare, but they exist. They exist in precisely the kind of environment where R136a1 was born, the dense, turbulent, gas-rich core of the Tarantula Nebula. What emerges from all of this is a picture of the upper mass limit, not as a clean boundary but as a contested zone. The Eddington limit sets a theoretical maximum luminosity for a given mass and composition. Opacity-driven instabilities enforce that limit through envelope pulsations and eruptive mass ejection. Radiatively driven winds continuously strip mass from the surface, grinding the star down over its lifetime. And the formation barrier resists the assembly of extreme masses in the first place, requiring specific environmental conditions to overcome. Each of these constraints has been quantified. Each has been modelled. Each predicts that stars above approximately 150 to 300 solar masses, depending on metallicity, rotation, and environment, should be exceedingly rare to the point of near impossibility. And yet, when astronomers pointed their most powerful instruments at the core of R136, they found a star sitting squarely in this contested zone, operating at 95% of its Eddington luminosity, shedding mass through a wind of extraordinary power and stubbornly refusing to fall below the theoretical ceiling. The issue is not whether physics permits such an object. Strictly speaking, it does at the extreme tail of every distribution, under the most favourable combination of every parameter. What remains unresolved is whether R136a1 can be accommodated by current models as a rare but explicable outlier, or whether its existence reveals specific shortcomings in our understanding of how extreme stars form, evolve, and interact with their environments. Answering that question requires examining not the general theory of stellar mass limits, but the specific observational facts of this particular star and the ways they strain or satisfy the predictions of modern astrophysics. That confrontation between theory and observation, played out in the dense core of a star cluster in another galaxy, is where the real story of R136a1 unfolds. The physics laid out in the previous section provides a clean theoretical framework. Radiation pressure fights gravity, stellar winds strip mass, opacity-driven instabilities enforce a ceiling, and formation barriers resist the assembly of extreme masses. Each mechanism is well understood in isolation. Each has been modelled, quantified, and tested against observations of massive stars across the Milky Way and beyond. The framework is elegant. The problem is that R136a1 does not fit neatly inside it. Not because it shatters the framework it does not, but because it simultaneously strains every component at once, in ways that expose the gaps between idealized theory and the messy reality of how the most extreme stars actually come into existence. The strain begins with a number that has haunted every research group that has studied this star: the birth mass. Whatever R136e1 weighs today, and the best current estimates place it near 200 solar masses, it was heavier when it was born. The star has been losing mass through its powerful wind since the moment nuclear fusion ignited in its core. The question is how much mass has been lost, and therefore how massive the star was at birth. This question sounds straightforward, but the answer depends on parameters that are among the most difficult to measure in all of stellar astrophysics. The mass loss rate of R136a1, derived from spectroscopic modelling, is approximately 5 × 10 to the -5 solar masses per year. The cluster is roughly 1 to 2 million years old. Multiply rate by time, and you get a crude estimate of total mass lost, between 50 and 100 solar masses, depending on which age estimate you adopt and whether the mass loss rate was constant or varied over the star's life. If the current mass is 200 solar masses and the star has shed 75, the birth mass was approximately 275 solar masses. If it shed 100, the birth mass approached 300. But this calculation assumes the mass loss rate has remained constant throughout the star's life, which is almost certainly wrong. When R136a1 was younger, it was more massive and more luminous. Higher luminosity drives a stronger wind. The mass loss rate in the first few 100,000 years of the star's life may have been significantly higher than the rate we measure today. Some evolutionary models suggest the wind was 2 to 3 times stronger during the star's early main sequence phase, when it was at peak mass and peak luminosity. If that is correct, the total mass shed over the star's lifetime could exceed 120 solar masses, pushing the inferred birth mass above 320. 320 solar masses is a staggering number. It sits at the absolute upper bound of what any current formation simulation can produce, and only under the most favourable conditions imaginable. Even the most optimistic three-dimensional radiation hydrodynamic models, those incorporating disk accretion, turbulent clump penetration, and the reduced opacity of a half-solar metallicity environment, struggle to assemble more than about 300 solar masses before radiation feedback terminates the accretion flow. A birth mass above 300 pushes against this ceiling with no room to spare. This is where the uncertainty in wind clumping becomes critically important. The mass loss rate derived from spectroscopic modelling is not a direct measurement. It is inferred from the strength of emission lines in the stellar spectrum lines produced when photons are scattered or emitted by ions in the outflowing wind. The strength of these lines depends on the density of the wind material. A denser wind produces stronger emission, but here is the subtlety. The emission from many diagnostic lines scales not with the density itself, but with the square of the density. This means that a wind composed of dense clumps embedded in a thinner interclump medium will produce much stronger emission than a smooth wind of the same average density. The clumpy wind mimics a higher mass loss rate. Wind clumping is parameterized by a factor usually denoted as F-cl, or its inverse, the volume filling factor. A clumping factor of 1 means the wind is perfectly smooth. A clumping factor of 10 means the wind material is concentrated into clumps that occupy 1/10 of the total volume, with the remaining 9/10 essentially empty. Because emission scales with density squared, a clumping factor of 10 would cause the spectroscopic analysis to overestimate the mass loss rate by a factor of the square root of 10, approximately 3.2. For R136a1, estimates of the wind clumping factor range from approximately 4 to 30 in different studies, with the most recent hydrodynamic models favoring values near the upper end of that range. This range is not a minor technical detail. It translates directly into an uncertainty in the mass loss rate of a factor of 2 to 4. If the clumping factor is near 4, the lower end of estimates, the mass loss rate is close to the spectroscopically derived value, and the birth mass implications remain extreme. If the clumping factor is near 20, the true mass loss rate could be less than half the nominal value, and the total mass shed over the star's lifetime drops significantly. A lower total mass loss means a lower birth mass, potentially bringing it down from 300 plus solar masses to something closer to 240 or 250. Still remarkable, but more comfortably within the range of modern formation models. Resolving the clumping factor is one of the most important observational challenges in massive star astrophysics. Different wavelengths probe different regions of the wind. Ultraviolet resonance lines form close to the star, where the wind is densest and clumping effects are most pronounced. Optical recombination lines probe intermediate distances. Infrared and radio continuum emission trace the outer wind, where the material has expanded, the density has dropped, and the filling factor approaches unity, meaning the wind is smoother. By comparing mass loss rates derived independently from ultraviolet, optical, infrared, and radio diagnostics, researchers can constrain the clumping structure. James Webb's infrared spectroscopy has begun this multi-wavelength calibration for R136a1. Early results suggest that the clumping factor in the inner wind is moderate, perhaps 8 to 12, implying that the nominal mass loss rate is overestimated by a factor of roughly 2. If confirmed, this would lower the inferred birth mass from the extreme 300 plus range to something closer to 250 to 270 solar masses. Still extraordinary. Still near the top of what formation models predict, but no longer requiring the absolute maximum theoretical mass to explain. Radio observations from the Atacama Large Millimeter Array are expected to provide additional constraints within the next few years by probing the smooth outer wind directly. These measurements are largely independent of clumping assumptions and will serve as a critical cross-check. If the radio-derived mass loss rate agrees with the clumping-corrected spectroscopic value, the birth mass question will be substantially clarified. If the values disagree, it will indicate that our understanding of wind structure in extreme stars is even less complete than currently assumed. While the mass loss history constrains the birth mass from the top down, the formation mechanism constrains it from the bottom up. Two competing hypotheses dominate the theoretical landscape for how a star like R136a1 could have been assembled, and they have very different implications for our understanding of star formation at the extreme. The first is competitive accretion. This model describes a process where protostars embedded in a dense, gas-rich cluster environment compete for material from a shared reservoir. Unlike the classical picture of isolated core collapse, where a single dense clump of gas collapses to form a single star, competitive accretion envisions star formation as a collective process. Protostars move through the cluster potential well, accreting gas from the surrounding medium. Those that happen to sit near the gravitational center of the cluster accrete preferentially, because material flows naturally toward the deepest point of the potential well. A feedback loop develops. The most massive protostar sits at the cluster center, attracts the most gas, grows more massive, deepens the local potential well, and attracts even more gas. Simulations of competitive accretion in clusters, with properties similar to R136 total mass, around 100,000 solar masses, half-light radius of roughly 1 parsec, embedded in a dense molecular cloud, have successfully produced individual stars with masses exceeding 200 solar masses. The key requirement is a high initial gas fraction. The cluster must begin with a substantial reservoir of unprocessed gas that has not yet been converted into stars. If the gas fraction is high enough, above 50% of the total cluster mass, the central protostar can continue accreting for several 100,000 years, reaching extreme masses before the gas is exhausted or expelled by feedback from the growing population of massive stars. The timescale matters critically. Competitive accretion works only if the gas supply lasts long enough for the central protostar to reach extreme masses. In less dense environments, feedback from massive stars ionizing radiation, stellar winds, radiation pressure on dust disperses the natal gas cloud within a few 100,000 years of the first massive stars igniting. This truncates accretion before any single object can grow beyond a few tens of solar masses. But in the extraordinarily dense core of the Tarantula Nebula, the gas column densities are so high that feedback takes longer to clear the reservoir. The cloud fights back. Dense filaments and clumps resist ionization and continue funneling material toward the cluster center, even as newly born massive stars pump energy into their surroundings. This extended accretion window is what allows the most extreme objects to form. The competitive accretion model makes specific predictions that can be tested against observations of R136. First, it predicts strong mass segregation. The most massive stars should be found at the cluster center, not distributed randomly. This is observed. R136a1 and the other hypermassive members sit in the innermost fraction of a parsec, exactly where the model places them. Second, it predicts a continuous mass distribution extending smoothly from the most massive star down through the rest of the cluster population. There should be no gap between R136i1 and the next most massive stars. This is also observed. The cluster contains a smooth distribution of masses from R136i1 at 200 solar masses down through R136i2 and a 3 at roughly 150 and 130 solar masses, continuing through dozens of stars in the 50 to 100 solar mass range. The mass function is steep but continuous, consistent with the competitive accretion prediction. The second formation hypothesis is stellar mergers. In a cluster as dense as R136, the probability of close gravitational encounters between massive protostars is not negligible. If two protostars, each already massive, perhaps 80 to 120 solar masses, pass close enough for their accretion disks or envelopes to interact, they can lose orbital energy through gravitational drag, spiral inward, and merge into a single object. The result is a star with a combined mass near or above 200 solar masses, created not through sustained accretion but through a single catastrophic collision. The physics of such a collision is worth pausing on, because it is unlike anything in ordinary human experience. When two massive protostars merge, the event does not resemble two solid objects smashing together. Stars are not rigid. They are gravitationally bound spheres of plasma, held in hydrostatic equilibrium by the balance between internal pressure and self-gravity. When two such objects approach each other within a critical distance, roughly a few stellar radii, tidal forces begin deforming both stars. The sides facing each other bulge outward as gravity from the companion pulls preferentially on the near hemisphere. The stars elongate, stretching into teardrop shapes as their outer envelopes reach toward each other across the narrowing gap. At some point, the tidal distortion becomes catastrophic. The outer layers of the two stars make contact, forming a bridge of superheated plasma connecting the two objects. Material begins streaming across this bridge, transferring mass from one star to the other. Orbital energy is converted into thermal energy through shocks and turbulent dissipation within the contact region. The two stars spiral inward on a timescale measured in days to weeks, extraordinarily fast by astronomical standards. The orbital decay accelerates as the contact region widens and more material participates in the energy dissipation. The final coalescence is violent. The two stellar cores plunge together, releasing gravitational potential energy equivalent to the total energy output of the Sun over millions of years compressed into a span of hours. This energy cannot escape the merged object quickly enough through radiation. Instead, it heats the stellar interior to extreme temperatures, drives powerful convective instabilities that churn the merged object from core to surface and inflates the outer envelope to many times its equilibrium radius. For a period lasting perhaps thousands to tens of thousands of years, the merger product is a bloated, overluminous, violently convecting object, structurally distinct from any star that formed through normal accretion. It gradually radiates the excess thermal energy, contracts toward thermal equilibrium, and eventually settles onto the main sequence as a single star, with a mass approximately equal to the sum of the two progenitors, minus whatever material was ejected during the merger itself. Hydrodynamic simulations of massive stellar mergers suggest that the mass ejected during the collision is modest, typically 5 to 15% of the total system mass. Most of the material remains gravitationally bound. A merger between two protostars of 100 solar masses each would produce a single object of roughly 170 to 190 solar masses, with the remainder expelled into the surrounding cluster environment as a rapidly expanding shell of hot gas. This expelled material would be enriched in CNO-processed elements dredged from the deep interiors of the progenitors during the violent mixing phase, potentially detectable as chemical anomalies in the surrounding nebula gas. Though separating this signal from the general chemical enrichment of the Tarantula Nebula remains a formidable observational challenge. N-body simulations of dense young clusters have explored this pathway in detail. Groups including those led by Samba and Banerjee at the University of Bonn ran simulations tracking the gravitational interactions of thousands of massive stars within cluster potentials matching R136. They found that in approximately 30 to 40% of simulations, at least one merger event occurred within the first million years, involving two stars each above 50 solar masses. In roughly 10% of cases, the merger product exceeded 150 solar masses. In a few percent, it exceeded 200. The merger pathway is not guaranteed for any individual cluster, but it is statistically expected for a population of clusters with the properties of R136. The merger hypothesis carries distinct observational signatures that distinguish it from competitive accretion. A merger product should exhibit chemical anomalies on its surface. Material from the deep interior of the progenitor stars, processed through CNO burning, gets dredged up and mixed into the outer layers during the violent collision. This produces elevated nitrogen abundance and enhanced helium mass fraction at the surface, compared to a star of the same mass that formed through smooth accretion and has not yet mixed its core process material outward. R136a1 does show elevated nitrogen and helium in its spectrum. The nitrogen-to-carbon ratio at the surface is significantly enhanced relative to the baseline composition of the Large Magellanic Cloud. The surface hydrogen mass fraction has dropped to roughly 40% down, from the roughly 75% expected for an unevolved star of its metallicity, with most of the remainder being helium-enriched through convective mixing from the core. These enrichments are consistent with the merger prediction. However, and this is an important caveat, similar surface enrichments can also be produced by rotational mixing in a rapidly rotating single star. If R136a1 was born spinning quickly, meridional circulation and shear instabilities in its interior would transport CNO-processed material from the convective core to the surface over its main sequence lifetime. Rapidly rotating models at 200 solar masses can reproduce the observed nitrogen and helium enrichment without invoking a merger. The chemical evidence is suggestive but not diagnostic. It cannot currently distinguish between the two formation pathways. There is another potential discriminant: the star's rotation rate. A merger product should initially spin very rapidly. The orbital angular momentum of the two progenitors gets converted into spin angular momentum of the merger product. However, the intense stellar wind of a 200 solar mass star carries away angular momentum as well as mass. Over 1 million years or more of wind-driven spin down, the merger product's rotation rate could decrease substantially, potentially erasing the observational signature. Current spectroscopic measurements of R136e1's projected rotational velocity suggest a value near 150 to 200 kilometers per second fast by normal stellar standards, but not extraordinarily so. This is consistent with either a rapidly born merger product that has spun down, or a single star born with moderate rotation. Again, the data do not cleanly distinguish the two scenarios. The honest assessment is that we do not know which formation pathway produced R136a1. Both competitive accretion and stellar mergers are physically plausible in the R136 environment. Both can produce objects at 200 or more solar masses. Both are consistent with the currently available observational data. It is even possible that both mechanisms contributed a star that formed through competitive accretion to 150 solar masses and then merged with a 60 solar mass companion, reaching a combined mass above 200. The formation scenarios are not mutually exclusive, and disentangling them will require observations that are at the very edge of current instrumental capability. One observational avenue that has received increasing attention is the broader population of the R136 cluster. If R136a1 is the product of a merger, there should be a corresponding deficit of one or two very massive stars in the cluster the progenitors were consumed in the collision. If it formed through competitive accretion alone, the mass function should extend smoothly and steeply down from the most massive star without any gaps or anomalies. Current star counts in the cluster are consistent with both possibilities, partly because the census of massive stars is still incomplete. Faint companions hidden in the glare of the brightest members, and intermediate mass stars embedded in nebular emission remain difficult to identify. Webb and future extremely large telescope observations will provide a more complete census, potentially revealing whether the cluster's mass function shows the statistical fingerprints of a merger event. Beyond the formation question, R136a1 challenges models through the sheer duration of its existence at extreme mass. Recall that stars near the Eddington limit are theoretically prone to violent instabilities, pulsations in the envelope, driven by opacity effects, episodic eruptions analogous to those observed in luminous blue variables, and strange mode oscillations that grow in amplitude and drive mass ejection. A star burning this close to its Eddington threshold should be teetering on the edge of instability throughout its life. What matters is what its existence is teaching us about the boundaries of stellar physics, and the answer, so far, is ambiguous. Spectroscopic monitoring of R136a1 over the past 2 decades has revealed variability in the strength of certain emission lines. Consistent with changes in the wind density or velocity structure, these variations occur on timescales of weeks to months and are modest in amplitude, nothing approaching the catastrophic eruptions seen in Eta Carinae. Photometric monitoring shows low-level brightness variations at the few % level, consistent with wind variability or surface pulsations. But no giant eruption, no sudden brightening by multiple magnitudes, no massive nebula shell indicating a recent ejection event has been observed. This could mean several things. Perhaps R136a1 is inherently more stable than theoretical models of Eddington limit stars predict. Some calculations suggest that the instabilities grow more slowly in hydrogen-rich WNH stars than in hydrogen-depleted classical Wolf-Rayet stars, because the hydrogen envelope provides additional stabilizing pressure. The pulsation growth timescales may be long enough that the star has not yet had time to develop a full-blown eruption, even over a million-year main sequence lifetime. Alternatively, the star may have erupted in the past, but the evidence has been erased. Ejected material would be swept up by the powerful cluster winds and incorporated into the Tarantula Nebula's general emission, distinguishing a shell ejected by R136a1 from the surrounding nebula gas itself, sculpted by dozens of other massive stars, supernova remnants, and wind-blown bubbles, is extraordinarily difficult. Infrared imaging from Spitzer, and now Webb, has searched for thermal emission from warm dust that might indicate a circumstellar shell ejected in a past eruption. The results are inconclusive. There is warm dust in the vicinity of R136, but attributing it to a specific star in such a crowded environment requires spatial resolution and spectral analysis that pushes current instruments to their limits. The extremely large telescope, with its factor of 16 improvement in angular resolution over Hubble, may be able to resolve circumstellar structures around individual stars in the R136 core. Until then, the question of whether R136a1 has experienced past eruptive mass loss remains open. There is one more dimension of tension that deserves attention: the statistical argument. The initial mass function, the distribution describing how many stars form at each mass, is one of the most fundamental empirical relationships in astrophysics. In its most commonly used form, the Salpeter initial mass function, the number of stars formed at each mass decreases as a power law with an exponent of -2.35. This means that for every star formed at 100 solar masses, roughly 10 stars form at 32 solar masses, 100 form at 10 solar masses, and 1000 form at 3.2 solar masses. The function is extremely steep at the high mass end. For a cluster with the total mass of R136, approximately 100,000 solar masses, the Salpeter function predicts a handful of stars above 100 solar masses. Finding one star at 200 solar masses is statistically improbable but not impossible, provided the mass function extends that high. The probability depends on how steeply the function drops above 100 solar masses and whether there is a physical truncation, a maximum mass above which no stars form at all, or whether the function simply continues as a power law to arbitrarily high masses with vanishingly small probabilities. Observations of R136 suggest that the mass function in this cluster may be shallower, less steeply declining at the high mass end than the Salpeter slope predicts. Several analyses of the cluster's stellar content find an excess of very massive stars relative to the standard power law. If real, this top-heavy mass function would make R136i1 less surprising. Instead of being a 1 in 10,000 outlier on the steep Salpeter tail, it would be a 1 in several hundred outlier on a shallower distribution, unusual but not alarming. Whether this top-heavy mass function is real or an artifact of observational incompleteness remains debated. Counting stars in the dense core of R136 is fiendishly difficult. Bright stars outshine their fainter neighbours. Nebular emission contaminates photometric measurements. Crowding causes blending, where two or more stars are mistaken for one. Each of these effects can bias the measured mass function, typically by causing an undercounting of lower mass stars relative to higher mass ones. If lower mass stars are missed, the mass function appears artificially top-heavy. Correcting for completeness requires detailed simulations of the observing conditions, and different groups using different correction methods arrive at different conclusions. The James Webb Space Telescope's infrared sensitivity and angular resolution have already improved the stellar census in R136, detecting lower mass stars that were invisible to Hubble in the optical. The resulting mass function from Webb data is closer to the Salpeter slope than earlier optical studies suggested, though a modest excess at the high mass end persists in some analyses. As the census becomes more complete, the statistical significance of R136e1's mass, whether it represents a rare but expected fluctuation or a genuine anomaly requiring special explanation, will become clearer. What emerges from this examination of R136e1's specific challenges to theory is not a single dramatic violation but a convergence of tensions across multiple domains. The birth mass is extreme but not demonstrably impossible, depending on the clumping correction. The formation mechanism is uncertain. Competitive accretion and mergers both work, but neither is confirmed. The predicted envelope instabilities are not clearly observed, but they may not have had time to manifest or their evidence may be hidden. The statistical rarity is real but model-dependent, hinging on whether the cluster mass function is truly top-heavy or merely incompletely sampled. No single tension taken in isolation would constitute a crisis for stellar physics. Taken together, they form a pattern. R136e1 pushes the limits of formation theory, mass loss physics, stability analysis, and population statistics at the same time. It does not cleanly violate any one prediction, but it requires every relevant model to operate at its most optimistic boundary at once. The birth mass must be near the maximum that formation models allow. The mass loss rate must be on the lower end of estimates, or the birth mass becomes unsustainably high. The stability must be greater than standard models predict, or past eruptions must be undetectable. The mass function must extend to higher masses than the salpeter slope favors, or R136a1 is a statistical anomaly of uncomfortable rarity. The framework holds, but it is being stretched to its limits across multiple fronts in parallel. And in science, when an object stretches every relevant model at the same time, it is usually telling us something not that the models are wrong, but that they are incomplete in ways that only the most extreme observations can reveal. The question, then, is not whether R136a1 should exist. It does exist. The question is what its existence is teaching us about the boundaries of stellar physics and how astrophysicists are using it to push those boundaries outward. That is where the story concludes. Science does not progress by confirming what it already knows. It advances when observations land in the narrow space between prediction and surprise objects that do not quite fit, measurements that fall just outside the expected range, phenomena that force a second look at assumptions so familiar they had become invisible. R136a1 occupies exactly this space. R136a1 occupies exactly this space, not outside the framework of stellar astrophysics, but at its outermost edge, and it does something productive from there. It reveals where that framework is built on approximations rather than certainties, where convenient assumptions have hardened into unexamined defaults, and where the physics we thought we understood completely still contains room for refinement. Every tension this star creates with formation models, mass loss prescriptions, stability predictions, and statistical expectations is not a wound in the body of theory. It is a diagnostic, a signal pointing toward the specific places where our understanding can be made sharper. The most consequential lesson R136a1 is delivering concerns mass loss rates in the most luminous stars. This might sound like a narrow technical detail, relevant only to specialists who model Wolf-Rayet atmospheres. It is not. Mass loss prescriptions are foundational inputs to stellar evolution codes, the computational tools that predict how stars of every mass live, age, and die. These codes are used to model not just individual stars, but entire stellar populations, galaxies, chemical enrichment histories, supernova rates, black hole formation channels, and the ionizing radiation budgets of the early universe. When an astrophysicist simulates the evolution of a galaxy from the Big Bang to the present day, the mass loss rates assumed for massive stars are among the most influential parameters in the calculation. Get them wrong, and every downstream prediction shifts. For decades, the standard mass loss prescriptions used in stellar evolution codes were calibrated against observations of massive stars in the Milky Way objects with roughly solar metallicity. The most widely cited prescription, developed by Jupp Vink and collaborators in the early 2000s, predicts mass loss rates as a function of luminosity, temperature, and metallicity using theoretical models of line-driven winds. These predictions have been broadly successful for stars in the 10 to 60 solar mass range, where numerous well-studied examples exist for calibration. But above 100 solar masses, the calibration becomes sparse. Very few stars in this regime have been studied with sufficient detail to test the prescriptions, and those that have, including R136a1, suggest that the standard formulas may need revision. The wind clumping problem, discussed at length in the previous section, is the primary source of this uncertainty. If clumping factors in extreme stellar winds are systematically higher than the values assumed when calibrating the Vink prescription, then the true mass loss rates for the most massive stars are lower than the standard formula predicts. Lower mass loss rates mean that massive stars retain more of their birth mass throughout their lives, arriving at the ends of their main sequence phases heavier than current models expect. This has cascading implications for every subsequent evolutionary phase: the helium-burning giant phase, the Wolf-Rayet phase, the final collapse, and the mass of the compact remnant left behind. R136a1 provides the most extreme test case available. Its mass loss rate has been measured using ultraviolet, optical, and infrared diagnostics, each probing different regions of the wind with different sensitivities to clumping. The multi-wavelength dataset from Hubble and Webb is the richest ever assembled for a star in this mass range. By comparing the rates derived at each wavelength and modelling the clumping structure that reconciles them, researchers are building the first empirically constrained picture of wind structure in a star above 150 solar masses. The results will directly inform the next generation of mass loss prescriptions formulas that will propagate through every stellar evolution code in the field. Early indications from Webb infrared spectroscopy suggest that the clumping-corrected mass loss rate for R136a1 is roughly a factor of 2 lower than the uncorrected spectroscopic value. If this finding holds across the broader population of very massive stars in the Tarantula Nebula, and the VLT Flames Tarantula survey is providing the data to test this, it would imply a systematic downward revision of mass loss rates at the highest luminosities. Stars above 100 solar masses would retain more mass, live slightly longer on the main sequence, and produce heavier remnants than current models predict. The correction is not dramatic. It does not overturn the basic physics of radiatively driven winds, but it shifts the quantitative predictions in ways that matter for black hole mass distributions, supernova energetics, and the chemical yields of massive star populations. The metallicity dependence of mass loss adds another dimension. Theoretical models predict that wind strength scales with metallicity lower metal content means fewer line-driving ions, weaker winds, and slower mass loss. This prediction has been tested observationally by comparing massive stars in the Milky Way, the Large Magellanic Cloud and the Small Magellanic Cloud, which span a factor of roughly 5 in metallicity. The observed trend broadly matches theory. Stars at lower metallicity lose mass more slowly, but the precise scaling, where the mass loss rate varies as metallicity to the power of 0.7 or 0.85 or some other exponent, remains debated, and the uncertainties are largest at the highest masses where the calibrating observations are fewest. R136a1, sitting in the half-solar metallicity environment of the Large Magellanic Cloud, anchors the high-mass, intermediate metallicity corner of this calibration space. Its measured mass loss rate, once the clumping correction is finalized, will provide a critical data point for refining the metallicity scaling. This matters profoundly for modeling the first generation of stars in the universe. Population: 3 stars, formed from primordial gas with essentially zero metallicity, should have had negligible line-driven winds. If the metallicity scaling is steep, these ancient stars would have retained nearly all their birth mass, dying as extraordinarily heavy objects and leaving behind black hole remnants of 100 solar masses or more. If the scaling is shallower, even trace amounts of metals produced by the very first supernovae could have driven significant winds in subsequent stellar generations, reducing remnant masses. The difference between these scenarios affects predictions for the seeds of supermassive black holes, the reionization history of the universe, and the gravitational wave signals expected from early universe black hole mergers. The formation question carries its own far-reaching implications. If R136a1 formed primarily through competitive accretion, sustained gas infall in a dense cluster core, it validates a formation pathway that should have operated even more efficiently. In the early universe, primordial molecular clouds were denser and more gas-rich than their modern counterparts, lacking the heavy elements that enable efficient cooling and fragmentation into many small protostars. Instead, early clouds may have collapsed into fewer, more massive objects, with competitive accretion channeling enormous quantities of gas onto a small number of growing protostars. Understanding how this process operates at Large Magellanic Cloud metallicity, where R136a1 provides a directly observable example, allows theorists to calibrate their simulations before extrapolating to the zero metallicity regime where no observations exist. If instead R136a1 formed through a stellar merger, The implications are different but equally significant. The merger pathway depends on cluster density rather than metallicity, which means it could operate at any epoch of cosmic history provided the stellar environment is dense enough. Some of the most puzzling objects in modern astrophysics might be explained by merger-formed extreme stars. Ultra-luminous X-ray sources in distant galaxies, objects that emit more X-ray radiation than any standard stellar mass black hole should be capable of producing, could be powered by black holes of 50 to 1. 100 solar masses, remnants of merger-formed stars that exceeded the normal mass ceiling. The pair instability mass gap, a range of black hole masses between roughly 65 and 120 solar masses, where standard supernova theory predicts no remnants should form, might be partially populated by the collapse products of merger-formed giants that followed unusual evolutionary pathways. Gravitational wave detectors have already identified merger events involving black holes in this mass range. The event GW190521, detected by LIGO and Virgo in 2019, involved a component of approximately 85 solar masses that sits squarely in the supposed gap. If stars like R136a1 routinely form through mergers in dense clusters, their remnants could explain these otherwise anomalous detections. The initial mass function question extends even further. Whether the distribution of stellar masses at birth is universal, the same everywhere, at all times, in all environments, or varies with conditions, is one of the most consequential open problems in astrophysics. A universal mass function enormously simplifies the modelling of stellar populations, galaxy evolution, and cosmic chemical enrichment. You measure the function once, apply it everywhere, and the predictions follow. A variable mass function complicates everything, requiring knowledge of local conditions to predict the stellar output of any given star-forming region. R136 and the broader 30 Doradus region offer the best available laboratory for testing universality at the high mass end. The cluster is young enough that its massive stars have not yet died, close enough that individual stars can be resolved and weighed, and rich enough that statistical analyses of the mass distribution are meaningful. If the mass function in R136 is genuinely top-heavy, producing proportionally more massive stars than the Salpeter power law predicts, it would constitute direct evidence for environmental variation. Such a finding would force revisions to every model that assumes a universal function, from estimates of cosmic star formation rates derived from galaxy luminosities to predictions of core collapse supernova rates in starburst environments. Current data are tantalizingly ambiguous. Some analyses of the R136 stellar census find a mass function slope shallower than Salpeter above 50 solar masses. Others, using different completeness corrections and binary assumptions, find consistency with the standard slope. The James Webb Space Telescope has improved the census by detecting lower mass stars that were invisible in optical surveys, partly filling in the denominator of the mass ratio. But the high mass end remains limited by small number statistics. There are only a handful of stars above 100 solar masses, and the statistical uncertainty on the slope of the mass function in this regime is inherently large. Definitive resolution will require not just better observations of R136, but comparable studies of other massive young clusters. The Arches cluster near the Milky Way's galactic center, Westerland 1 and 2 in the Carina Arm, NGC 3603 in the Carina Nebula, and similar objects in nearby galaxies. Building a sample of clusters with well-measured high-mass populations is the only path to determining whether R136 is typical or exceptional. Future observational facilities will transform every aspect of this investigation. The European Southern Observatory's extremely large telescope, expected to achieve first light within the next few years, will bring a 39-meter primary mirror to bear on the Tarantula Nebula. Its angular resolution, 16 times sharper than Hubble in the optical, will resolve individual stars in the densest regions of the R136 core that currently blur together even in space-based imaging. Stars that appear as single objects today may resolve into close binaries, altering mass estimates. Faint intermediate mass stars currently lost in the glare of their luminous neighbours will emerge from the background, completing the cluster census and tightening the mass function measurement. Spectroscopic observations with the ELT's high-resolution instruments will measure radial velocities, rotational velocities, and chemical abundances for individual cluster members with precision that is currently impossible. These data will constrain binary fractions, rotational distributions, and chemical mixing histories, each of which bears on the formation and evolution of R136a1. The James Webb Space Telescope will continue providing infrared spectroscopy and imaging that penetrates the dust and nebula emissions surrounding the cluster. Multi-epoch observations spread over years will track variability in R136a1's wind structure, searching for the slow pulsations and episodic mass loss events that theory predicts for stars near the Eddington limit. Even the non-detection of variability above a certain amplitude would be scientifically valuable, placing upper limits on the instability growth rates and constraining the physics of radiation pressure-dominated envelopes. The Vera C. Rubin Observatory's legacy survey of space and time will monitor the Magellanic Clouds photometrically every few nights for a decade, creating an unprecedented time-domain record of massive star behavior. While R136a1 itself is too bright for Rubin's detectors without saturation, the dozens of other massive stars in the 30 Doradus region will be monitored continuously. Any eruption or major mass loss event in this population would provide direct observational evidence of the instabilities predicted for Eddington limit stars, calibrating the theoretical models in real time. At longer wavelengths, the next generation Very Large Array and upgrades to the Atacama Large Millimeter Array will measure the radio and submillimeter continuum emission from massive stellar winds, with sensitivities far beyond current capabilities. These observations probe the outer, smooth regions of the wind where clumping effects are minimal, providing mass loss rate estimates that are essentially independent of the clumping corrections that plague ultraviolet and optical analyses. Cross-calibrating mass loss rates across the full electromagnetic spectrum from the far ultraviolet through the radio will deliver the definitive empirical constraints needed to resolve the clumping problem and finalize the mass loss prescriptions for the most massive stars. Gravitational wave astronomy opens yet another window. R136a1 will exhaust its fuel in a cosmically brief span, almost certainly collapsing to form a black hole. The mass of that remnant depends on the star's final mass at the moment of collapse, which in turn depends on the cumulative mass lost through winds and any late-stage eruptions. Current estimates suggest the remnant could range from roughly 40 to over 80 solar masses, depending on the details of the pre-collapse mass loss history and whether the star undergoes a successful supernova explosion or collapses directly without significant mass ejection. Black holes in this mass range fall within or near the upper mass gap predicted by pair instability supernova theory. In stars with helium core masses between roughly 65 and 130 solar masses, explosive oxygen and silicon burning produces electron-positron pairs that soften the equation of state, triggering violent pulsations or a complete thermonuclear disruption that leaves no remnant. This pair instability mechanism should create a gap in the black hole mass spectrum. No remnants between approximately 50 and 130 solar masses. Yet LIGO and Virgo have detected merging black holes with component masses in this range. If stars like R136a1, with their extreme masses and unique evolutionary pathways, can produce remnants that populate the gap perhaps through direct collapse that bypasses the pair instability regime, or through late-stage mass loss that shifts the helium core mass below the pair instability threshold, they would provide a natural astrophysical explanation for the gravitational wave observations. The broader significance of extreme stars like R136a1 extends beyond the technical details of mass loss rates and formation mechanisms. These objects are the dominant engines of cosmic chemical evolution. A single star at 200 solar masses during its brief lifetime produces more ionizing photons than 1,000 sun-like stars will produce in their entire 10 billion year existences. Its ultraviolet radiation carves cavities in the interstellar medium, spanning hundreds of light years. Its powerful wind injects mechanical energy into the surrounding gas, driving shocks that compress clouds and trigger new rounds of star formation. When it finally explodes or collapses, it enriches its surroundings with heavy elements forged in its core: carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron group elements that will be incorporated into the next generation of stars and planets. During the first few 100 million years after the Big Bang, when the universe was transitioning from a dark neutral fog to the transparent ionized cosmos we observe today, massive stars were the primary agents of this transformation. Their ultraviolet radiation ionized the intergalactic hydrogen, creating the vast bubbles of ionized gas that eventually merged to complete the epoch of reionization. How many of these early stars existed, how massive they were, and how much ionizing radiation they produced are critical inputs to models of reionization. If the upper mass function extends higher than classical predictions assumed as R136a1 suggests, it might then fewer total stars would have been needed to complete reionization. The ionizing photon budget of the early universe would have been dominated by a smaller number of extreme objects rather than a larger population of moderately massive stars. This shifts predictions for the timing, topology, and observational signatures of reionization in ways that upcoming 21 centimeter hydrogen observations with facilities like the Square Kilometre Array may be able to test. There is a philosophical dimension to this story that deserves acknowledgement not because it changes the physics, but because it shapes how we interpret what R136a1 means for our understanding of the cosmos. For most of the history of stellar astrophysics, the upper mass limit was treated as a relatively firm boundary. Textbooks stated it cleanly: stars above 150 solar masses cannot exist. The number was presented with the confidence of a physical law, like the speed of light or the charge of an electron. Students learnt it, researchers assumed it, models were built on it. R136a1 did not prove that number wrong. What it demonstrated is that the number was never as firm as its presentation implied. The upper mass limit was always a probabilistic statement, a prediction about where the likelihood of star formation drops below some threshold, not a hard physical wall where formation becomes impossible. The Eddington limit defines a luminosity ceiling, not a mass ceiling. The relationship between mass and luminosity depends on composition, rotation, and evolutionary state. The mass loss rate that grinds stars down toward the limit depends on metallicity, clumping, and episodic eruptions. The formation barrier that resists the assembly of extreme masses depends on cloud density, turbulence, and accretion geometry. Every link in the chain carries uncertainties, and those uncertainties compound. The firm number in the textbook was always an approximation, a useful central estimate surrounded by a broad zone of genuine physical uncertainty. That realization is science operating exactly as it should. Approximations are essential tools. They allow progress in the absence of complete information. The 150 solar mass limit enabled decades of productive research by providing a workable framework within which models could be built and tested. But approximations must eventually be confronted with observations, and when they are, the boundaries of knowledge shift. R136a1 is the observation that forced the confrontation. The result is not that the framework collapses, but that it becomes more nuanced, more honest about its own limitations, and ultimately more accurate. The scientific community's response to R136a1 has been exemplary in this regard. There has been no crisis narrative, no claim that stellar physics is broken, no rush to invoke exotic new physics. Instead, there has been a systematic effort to refine every relevant measurement and model. Mass loss prescriptions are being recalibrated. Formation simulations are being run at higher resolution with more realistic physics. The initial mass function is being measured more carefully in extreme environments. Wind clumping is being constrained through multi-wavelength observations. Each effort chips away at the uncertainties, narrowing the gap between observation and theory. This is how astrophysics matures, not through dramatic revolutions where old theories are discarded wholesale, but through incremental refinements driven by objects that push models to their limits. Neutron star mass measurements drove improvements in nuclear equations of state. Black hole spin measurements refined models of accretion disk physics. Exoplanet discoveries transformed theories of planetary formation and migration. In each case, the observation did not invalidate the theory. It revealed where the theory was approximate and motivated the work needed to make it precise. R136a1 is playing the same role for stellar mass limits, mass loss physics, and massive star formation theory. The star that headlines said should not exist does exist. It burns in the core of the most violent star-forming region in the local group, 200 times the mass of our Sun, 6 million times as luminous, hemorrhaging material through a wind that races outward at several thousand kilometers per second. It operates just below the luminosity that would tear it apart. It challenges the classical mass ceiling not by smashing through it, but by standing on it, balanced at the edge of what physics permits, daring models to explain exactly how it got there and how long it can remain. Within the next 1 to 2 million years, a blink in cosmic time, R136a1, will exhaust the hydrogen fuel in its core. It will evolve off the main sequence, inflate, shed additional mass through increasingly violent winds and eruptions, burn helium, then carbon, neon, oxygen, and silicon in a sequence of ever shorter nuclear burning phases that compress billions of years of solar evolution into a few 100,000 years. At the end of this sequence, the core will collapse. Whether it produces a brilliant supernova visible across the local group or quietly swallows itself into a black hole without significant explosion depends on the mass and angular momentum of the core at the moment of collapse. Parameters that are themselves functions of the mass loss history we are still working to constrain. Either way, R136i1 will leave behind a compact remnant that carries the imprint of its extraordinary life. A black hole born from this star will be among the most massive stellar mass black holes in the universe, a gravitational fossil preserving information about conditions at the extreme edge of stellar physics. We cannot watch this unfold. 2 million years is far longer than any human institution will persist. The civilizations that witness R136i1's death, if any exist, will be unrecognizably different from our own. But we can observe the star now, at this moment in its life, and extract from its light every piece of information that physics allows. Each spectrum, each photometric measurement, each infrared image is a message from the contested boundary where radiation fights gravity to a standstill. Decoding those messages is teaching us not just about one extraordinary object, but about the processes that govern the most massive stars throughout the cosmos and across cosmic time. R136i1 means our models are still being written. The equations that describe stellar structure, radiation transport, nuclear energy generation, and mass loss are correct in their foundations. But their application to the most extreme objects requires calibration that only the most extreme objects can provide. This star burning at the edge of its own destruction, shedding itself into space, illuminating the Tarantula Nebula with the light of 6 million suns is the calibration point. It sits exactly where our knowledge ends and our questions begin. And in science, that boundary is not a place of failure. It is the most productive place there is. The most extreme star ever found does not invalidate what we know. It sharpens what we know. It reveals where approximation masquerades as certainty. It demands better measurements, better simulations, better theory. And in demanding those things, it pushes astrophysics forward not through crisis, but through the quiet, persistent pressure of an observation that refuses to be fully explained by the models of today. That pressure is not a threat to physics. It is the engine that drives physics. It always has been. And in the Tarantula Nebula, burning with the luminosity of 6 million stars, R136e1 is applying that pressure right now.